Let's get started. Last time we talked about the absorption, and we mentioned that the aggregate, it has voids that can absorb water. And according to this, we have four moisture conditions. We have the bone dry, we have air dry condition, and we have saturated surface dry, and we have moist aggregate. And in order to determine the specific gravity, today we are going to talk about the specific gravity, one of the most important aggregate property. And the specific gravity is going to depends on the moisture conditions. Since we have four moisture conditions, it means that the specific gravity also is going to we are going to have four types of specific gravity, and it's going to be defined based on how voids in the aggregate particles are considered. So what is the importance of the specific gravity? The specific gravity, it's not indicator, it's not important indicator of aggregate quality, but they are important for concrete mix design. Later on, we will learn how to come up with concrete mix design. And in order to do that, you need to know the specific gravity of the coarse aggregate and the fine aggregate. But the values of a specific gravity is not indicator whether the aggregate is good or bad. Generally, the specific gravity here is going to be defined by the mass of the material or the mass of the aggregate divided by the mass of an equal volume of water. We are going to use the mass of an equal volume of water because we are going to find out that the volume of the aggregate itself, it's difficult to determine due to the nature of the aggregate. And we are going to focus only on the three types of specific gravity. We have the bulk dry specific gravity, we have the bulk saturated surface dry specific gravity, and we have the apparent specific gravity. So in general, the specific gravity is going to be the weight of the aggregate over its volume, and this one represents the density of the aggregate over the density of the water. So we have here three types, like I said, because of the voids. Here the voids inside the aggregates. We have permeable voids, which mean that these voids could be filled by the water. And here we have the impermeable voids. These voids here cannot be filled by the water. And we have the solid part. So in the bulk dry specific gravity, since it's dry here, we are going to measure only the dry weight. We are not going to consider the water inside the voids. So in this case, in the case of bulk dry specific gravity, we are going to measure only the dry weight, this one only here. We are not going to consider the weight of the water inside the permeable voids. And then over the total particle volume. And regarding the volume, we have the volume of the solid, Vs, and we have the volume of I, the volume of the impermeable voids, this volume here, and we have Vp, the volume of permeable voids. So in the dry specific gravity, we are going to include all the volumes, the total particle volume. And regarding the bulk saturated surface dry, the only difference here is Wp. Wp represent the weight of the water inside the permeable voids. Okay, so the only difference between the bulk dry specific gravity and the bulk SSD specific gravity is Wp, and Wp is the weight of the water inside the voids here. Okay. And finally, we have the apparent specific gravity. The apparent specific gravity is similar to the bulk dry specific gravity, except that we are not going to determine the volume of the permeable voids. The volume of the permeable voids will not going to be counted. Okay, so it depends on how the voids here, depends on the voids of the aggregate. we are going to have three types of specific gravity. Okay, remember the specific gravity is the gamma of the material over the gamma of the water, and the gamma of the material is the weight of the material over the volume of the material. So the problem here, to determine those values, Vs, like you can see here, in order to determine the volume of the solid and the volume of the permeable voids and the volume of the impermeable voids, it's difficult to do that. That is why we are going to use the water in order to do this. We are going to use the water. Those who has been in the lab last week, in order to determine the specific gravity, we measure the weight of the aggregate inside the water and the weight of aggregate in air. Okay, so we need to know why we use the water. So let's focus here. We say that the specific gravity is gamma solid or gamma object. Here we are going to say that we are going to have gamma aggregate over gamma water. So gamma aggregate is mass of the aggregate over the volume of the aggregate, while the gamma water is the mass of the water over the volume of the water. You can take the volume of the solid or the volume of the aggregate with the volume of the water, but in this case, this volume should be similar to that volume. In other words, the mass of the water here, it should be the mass of the water displaced by the volume of the aggregate. In that case, the volume of the aggregate is going to be similar to the volume of the water. So if you want to use this formula here, the mass of the solid over the mass of the water displaced by the volume of the aggregate, in this case, we are going to measure the aggregate inside the water, and also we are going to measure the aggregate in the air. So now mass water is going to be the weight in the air minus the weight in the water. In order to understand this, I'm going to show you this example why we should weigh on the water. Assume that I have this container. We have a volume of the water equal 400 milliliter, and the mass of that water is going to equal 400 gram. Also, you need to remember this. The density of the water is 1 gram per milliliter. Okay, the density of the water is 1 gram per milliliter. So if you are going to have, if the volume of the water is 400 milliliter, it means that the mass should be 400 gram. It's a property in the water. Then assume here I have aggregate in this container, and the volume of the aggregate, if I'm going to know the volume of the aggregate here, the volume is 250 milliliter and the mass is 500 gram. Okay, now here they give us the volume of the aggregate. We know that determining the volume of the aggregate is difficult, but let's say that here we know the volume of the aggregate. Now it's required to determine the specific gravity. In this case, the specific gravity is very easy since I know all the volumes and all the masses. So in this case, I'm going to say that the density of the aggregate is going to be the mass over the volume, which is 2 in this case, and the density of the water is 1. So in this case, the specific gravity is density of the material over the density of the water, and in this case the value came out to be 2. So this is the direct solution in case you know the volume of the aggregate, but it's difficult to know the volume of the aggregate, so we are going to put the aggregate inside the water. So if you are going to put the aggregate inside the water, assume that here the volume of the water is 400 milliliter, and here the volume of the aggregate is 250 milliliter. That means now the volume is going to be this one plus this one, which is 650 milliliter, right? So now the volume is 650 milliliter. Now, because I put the aggregate here, amount of the water is going to be displaced, because I put the aggregate here, then the a mass of the water has been displaced here. Okay, and we need to know the volume of the water here in that case. So the volume of the water here is going to be 250 milliliter. Why? Because the volume of the water displaced here is going to be the same as the volume of the aggregate. Okay, so the volume of the aggregate here is going to be the same as the volume of the water which has been displaced in this place. So since the volume of the water here is going to be the same as the volume of the aggregate, which is 250 milliliter, and we know that the density of the water is 1 gram per milliliter, it means that the mass of the aggregate is going to be 250 gram. Since the volume is 250 milliliter, it means the mass of the water is going to be 250 gram. Okay, and this here represent the mass of the water displaced by an equivalent here represent the mass of the water displaced by equivalent amount of the volume of the aggregate. So now we need to get the same solution, but this time using the mass of the water displaced by the aggregate. We know that the mass of displaced water, it could be equal the volume of displaced water times the density of the water. The density of the water, of course, is the mass over the volume. So this one over that one, it will give you the mass of displaced water. Now we put it in this formula. But we know that the volume of displaced water here is similar to the volume of the aggregate, right? So we know that the volume of the water is the same as the volume of the object, and the object here in this case is the aggregate. We can say that the mass of the water represents the volume of the object times the density of the water. So in this case, if I'm going to know the mass of the water, I will be able to know the volume of the object times the density of the water. So remember this. Here I have the volume of the object times the density of the water. If you get to the formulas here, all of them here, you have the volume of the particle over gamma water. So this part here now represent the mass of water displaced by the volume of the aggregate. So I'm going to replace all of this by the mass of water. That is why we weigh in the water. So now, in order to apply the indirect solution, the specific gravity is going to be the mass weighed in the air over the displaced water by an equivalent amount of volume. And in this case, the mass of the water is going to be the weight in air minus weight in water. Okay, so now let's look at how we are going to determine the specific gravity of the coarse aggregate. So to do that, we need to use this basket here with a bucket of water. We are going to place the aggregate inside this basket here to measure the aggregate in the water. And also we need to determine the SSD condition. And finally, we need to determine the dry sample. And that could be done by put the aggregate inside the ovens until we get a constant weight. So in order to determine the bulk dry specific gravity, I need to know the value of A. The value of A is dry weight. The value of B is SSD weight. And the value of C is the weight of the aggregate inside the water. If I know A, B, C, I'll be able to determine bulk dry specific gravity, bulk SSD specific gravity, and apparent specific gravity, and also the absorption. Okay, we have done this in the lab, if you do remember that. And similarly, we are going to also determine the specific gravity of fine aggregate. This time, because the aggregate, the fine aggregate, cannot be put in basket like this one. So here we need to introduce additional letter. We are going to use a pycnometer, this one here. I'm going to fill the pycnometer with a water to a certain level. Then I'm going to measure the weight of the pycnometer with the water. Then I'm going to place the sand inside the picnometer, and I'm going to measure again. The difference between them represent the weight of the sand inside the water. That is why we added additional letter. But the concept here is going to be similar to the concept there. Okay. And also, one of the important property regarding the aggregates, we have the bulk unit weight. So what does it mean by the bulk unit weight? So in order to make concrete mix, you need to know how much the weight of the aggregate inside a container of a unit volume. So the bulk unit weight is the weight of the aggregate required to fill a unit volume. So assume here I have a unit volume, and I'm going to fill the aggregate, the container with the aggregate. Then I'm going to determine the bulk unit weight. So the bulk unit weight is going to be the weight of the aggregate over the volume of the container. So we are going to measure the weight of the container here, and also we need to determine the weight of the container plus the weight of the aggregate. I'm going to subtract this one from that one to get the weight of the aggregate, and I should know the volume. So according to the ASTM C29 procedure, also we have done this test in the lab. We determine two types of bulk unit weight. We determine the loose bulk unit weight, which means that we fill the aggregate inside the container without rodding, and we also determine the rodded bulk unit weight, and in that case we rodded the aggregate inside the container. So in order to then determine the bulk unit weight, I need to use a rigid container of a known volume, and it should be filled with aggregate, and it should be compacted either by rodding, jigging, or shuffling. Also, if I know the determine the bulk unit weight, also I'm going to be interested to determine the voids inside the container, because the container is going to contain voids here. So how I'm going to do that? So I have container. I fill the container with aggregate. I need to determine the value of the voids. So if I do know the value of the solids, I'll be able to determine the value of the voids, right? So the value, the percentage of the voids is going to be 100% minus the percentage of the solid, which is the aggregate. So in this case, I'm going to first to determine the volume of the solid. Then the volume of the voids is going to be 100% minus the volume of the solid. So how I'm going to determine the volume of the solid? The volume of the solid is going to be the volume of the solid, this one here, over the volume of the container. And if you do recall here, in order to determine gamma bulk is the weight of the solid over the volume of the container, right? So instead of the volume of the container, I'm going to put the weight of the solid over gamma bulk. And the volume of the solid is going to be the weight of the solid over the density of the solid itself. So the W here goes with the W there. I'm going to end up with gamma bulk over gamma solid. Gamma bulk, I'm going to calculate it from here. From here, I will be able to determine gamma bulk. But what about gamma S? We know that gamma S is going to be the specific gravity of the solid times gamma W. We explained how to determine the specific gravity. So now if I do know the specific gravity of the solid, and I do know the bulk unit weight, I'll be able to determine the percentage of the volume of the solid. And if I manage to do that, I'll be able to determine the percentage of the voids. So now let's see example here. We have coarse aggregate, which has been placed in a rigid bucket. So here we have a rigid bucket, and then coarse aggregate has been placed there. And we provide rodding compaction, okay, with a taping rod. So we have a rod, in order to do compaction. And it's required to do the following. It's required to calculate the dry roded unit weight. It's required to determine the dry roded unit weight. So here it's required to determine the bulk unit weight, but it should be roded. Okay, and it's given the volume of the bucket. So we know the volume of the bucket. We know the weight of the empty bucket. And also we know the weight of the bucket filled with dry roded coarse aggregate. So now we want to determine the dry roded unit weight. So I'm going to use this formula here. So we are going to say that the dry rod unit weight is going to be the weight of the solid, and the weight of the solid in this case is going to be this value minus that value, because I need only the weight of the solid. So this one is the weight of the solid plus the bucket, and this one is the weight of the empty bucket. So this one minus that one is going to give me WS, and the volume of the bucket is given here. So this one over that one is going to give me the bulk unit weight, but this time should be a dry roded unit weight. And in the second part of this example, they say that if you do know the specific gravity of the aggregate, so here he give us GSB. He wants you to determine the percentage of the voids in the aggregates. In this case, we are going to use this formula here. We use this formula first to determine the percentage of the solid, this one, and then I'll be able to determine the percentage of the voids. So I'm going to use this formula. Do I know gamma B? Yes, I determine gamma B. Do I know GSB? Yes, it's given, and I do know the value of gamma water. So I'm going to use this formula. You know this value, which is here, GSB, which is there, and gamma water in pound per cubic foot is going to be 62. So do not forget this. So this one is going to be 62.3. This one from here, and this one from there. So this one represents the percentage of the solid. If this one is the percentage of the solid, that means the percentage of the voids is going to be 100% minus this percentage, which is 31.5%. Finally, we have the strength and the modulus property of the aggregate. This is not important property because it's difficult to test the strength of the aggregate. It's difficult to determine the strength of the aggregate, and the strength of the Portland cement concrete and the asphalt concrete cannot exceed that of the aggregate. So the strength of the aggregate is going to be larger than the strength of the concrete and the strength of asphalt concrete. And the aggregate strength is generally important in high strength concrete. We have a special type of concrete. We call this type high strength concrete. That means the concrete is going to have a higher strength than the normal concrete. In this case, it's very important to know the strength of the aggregate. But generally, it's not important to know the strength of the aggregate. And the tensile strength of the aggregate ranges from 0.7 megapascal to 16 megapascal, while the compressive strength ranges from 35 megapascal to 350 megapascal. And the modulus of elasticity of aggregate is not not usually measured. So that is why this property is not important. But you need to know one of the most important properties in aggregate is the aggregate gradation. So aggregate gradation, we are going to know the distribution of the aggregate. We know that the aggregate have different sizes. So we need to know the distribution of the aggregate, because this one is going to affect a lot of qualities like the density and the percentage of the fine aggregate and the coarse aggregate, and many properties. So aggregate gradation describes the particle size distribution. And in order to do this, we are going to use the sieves. We have seen all of this in the lab. So we are going to use a number of sieve in a descending order, which means that the largest opening, this one is going to be the first, and then the size of the opening is going to be increased, and at the bottom we are going to have the smallest opening. So we are going to arrange the sieves so that the sieve with the largest opening is going to be on the top, while the sieve with the smallest opening is going to be arranged on the bottom. Then we are going to take a representative sample of the aggregate. We are going to put it here, and then we are going to shake the series of the sieves here, there, so that I can know the distribution of the aggregate. As a result, every aggregate is going to retain on its own sieve. Okay. Then I'm going to measure all the aggregates there, and I'm going to come up with the relation between the percentage passing and the size of the aggregate. So this process is going to be evaluated by passing the aggregates through a series of sieves. Here we have a series of the sieves. Then the aggregate should go through this process, and then the sieve retains particles larger than the opening, while smaller ones pass through. Okay, so if the aggregate is larger than the opening, is going to retain here. If the aggregate is smaller than the opening, is going to pass to the next sieve, and so on until you finish the process. In order to determine the sieve analysis for the coarse aggregate, here we are going to use those sieves there. We are going to have a sieve, 4-inch sieve, up to number 16. Of course, it depends on your situation. You can, for example, if you know the largest aggregate sieve, you can, for example, start from here or start from there. Okay, so it depends on the condition of your aggregate, but generally we are going to use those sieves in order to evaluate the coarse aggregate. And in order to evaluate the fine aggregate, we are going to use those sieves. We are going to start with 3/8-inch sieve up to sieve number 200. In the lab, in the last Thursday, we used this sieve here, this one, this one, this one, and this one, and that one, in order to conduct the sieve analysis for the coarse aggregate. Okay, and also you can determine the sieve analysis for the fine aggregate using those sieves. So which one is better? Is it better to have aggregate with a large particle, or is it better to have aggregate with the small particle? Let's see what is the benefit of this case and that case. So assume that you are going to use aggregate with the large particles. So focus on the surface area. So this one is going to be the surface area, right? We know that we are going to use the aggregate in order to produce concrete. And in order to produce the concrete, you are going to use the cement. The cement is going to bind the aggregates together. And the cement is going to be located on the surface of the aggregate. Now, here I have the surface of the aggregate. What if I break the aggregate into two parts, part A and part B? Now, what will happen to the surface area? So if this one is the surface area, now the surface area is going to be larger than this one, which means that now I'm going to consume more binder, more cement in this case and in that case. So if I'm going to use large aggregates, it means that I'm going to use less binder, which is economical advantages. Okay, so if I'm going to use large aggregates, it means that I'm going to use less binder, less cement. But we have a problem with the large aggregates. Like you can see here, we have, let's say, a foundation here, a raft foundation, and of course in reinforced concrete, we use steel bars. So here we have steel bars in X and in Y. And we have a distance between the bars in X and in Y. So assume that I used a large aggregate. Then when I'm going to bump the aggregate inside the site here, if the size of the aggregate is big, it's going to stuck here. If the aggregate is going to stuck here, that means it's going to form voids inside my concrete, and that is going to reduce the strength of my concrete. So if you want to use a large aggregate, just make sure that the aggregate is not going to be larger than the spacing of the parts. Okay. So like I say here, after I finish from the sieve analysis test, I'm going to come up with this plot. In x-axis, I have the sieve size. Okay, here I have 50 millimeter opening, and here I have 0.075 opening, size opening. This one represent sieve number 200, and this one here represent 2-inch sieve. Okay, so now I need to determine the percent passing. We'll learn how to do that, and here I'm going to show you example how to determine the percent passing. So I need to create relation between the percentage passing and the sieve analysis. But this one here is a semi-log graph. Why it's a semi-log graph? Because the graph here, if I'm going to make it normal, is going to be too long. Okay, because the difference between 50 and 0.075 is going to be large. That is why we are going to use the log scale in x-axis. But regarding the y-axis, we are going to use normal scale. So this one is log scale and this one is a normal scale. So we are going to call it semi-log graph. So depends on how the curve is going to be plotted. We are going to say that this aggregate here, it has good distribution or not. Okay, so let's see example here. We need to conduct a sieve analysis test on a sample of fine aggregate. So we have fine aggregate. We are going to use this set here. Okay, like I said, that depends on your situation. You can start with this one or that one or that one. So in this case, we are going to start with sieve number 4. So in this example, we need to conduct sieve analysis for fine aggregate. Then we are going to start with sieve number 4. This one is sieve number 4, and this one is sieve number 200. Then I'm going to put the sieves in order, in descending order, and I'm going to take representative sample of this fine aggregate, and then I'm going to check the sieves, and as a result, the aggregate larger than the sieve is going to return on the sieve, and the aggregate smaller than the sieve is going to pass through the sieve. Then I'm going to measure the amount returned on each sieve. For example, in sieve number 4, we didn't retain any amount, which means that all the particles have been passed through sieve number 4, and so on. I'm going to measure all the aggregate retained on each sieve. Then I need to determine the percentage passing. Like you can see here, I need, in order to come up with this graph, I need to know the percentage passing. So in order to determine the percentage passing, first here I have the sieve size. I'm going to create like 1, 2, 3, 4 columns. The amount retained is given. It's from here. Then I'm going to determine the cumulative amount, which means that the cumulative amount retained here and there and there. So if this one is 0, this one is going to be 0. The value here is going to be this value plus that value. So 0 plus 33.2. And this value here is going to be 0 plus 33.2 plus 56.9, and so on until I finish. So the last number is going to be the total amount of the fine aggregate. Then I'm going to determine the percentage of the cumulative amount. So the percentage is going to be this value over the total, this value over the total, and this value over the total. Okay, So the last one is going to be 100%. Then in order to, if this one is a cumulative percentage return, it means that the percentage passing is going to be 100 minus this value and so on. Okay, so the value here is going to be 100% minus 6. The value there is going to be 100% minus 18. Even though in the lab we did it in different way, so you can do the process in different ways, but at the end you need to come up with the percentage passing. Then after I finish from the percentage passing, I'm going to plot the graph between the sieve size and the percentage passing. So here I have the sieve size and I have the percentage passing. I'm going to connect this point, and I'm going to come up with the graph. Then if I manage to do that, I'll be able to judge whether the aggregate has a good distribution or not. So next time we are going to talk about the types of the gradation. We have aggregate with a high density gradation, we have aggregate with one size gradation, we have aggregate with a gap graded, and we have aggregate with open graded. So next time we are going to know how to classify the type of the aggregate depends on that curve. So I'm going to stop here. If you have any questions, please ask me.